This video tutorial is going to show you how to go through your dye binding assay TF data that was given to you in Blackboard so that you can pretty much end up with one final value of moles of GAPDH in the DTNB reaction, which you're going to use in conjunction with your answer from prompt B3 to figure out how many moles of, or sorry, I should say how many cysteine residues there are in per GAPDH molecule or GAPDH protein. All right, so this is pretty much going to be one of the longer videos because I'm going to go through prompts B4 all the way through B8, and but I do have in the description all the different time marks for all the different prompt designations, so you can go ahead and skip forward or go back as you need to do. So the dye binding data that I gave you in the Chapter 9 BTF data in the Excel spreadsheet, it's going to look like this. You use these values up here to find out your own extinction coefficient to figure out how many sulfhydryl moles of sulfhydryl groups there was in the entire DTNB reaction. These first values here are the standard curve tube readings that we've generated for you for your TF data. And so basically the only thing that you need to do here is, what you're going to do for B4 is create a data table for this. And so essentially you're going to take this data and, generate a data table. The only thing that's missing here is the actual micrograms of BSA, because if you remember, for a typical standard curve, we plot the absorbance values on the y-axis and the corresponding micrograms of BSA on the x-axis. So I'll go ahead and put that there as another column, but it's not included in your TF data. How to calculate the micrograms of BSA. If we know that we have a 1 mg per mil or 1 microgram per microliter solution of BSA, and we know the microliters, the volumes that we put in there, we could just essentially use those two pieces of data to figure out the total mass of BSA that went in there. So 1 mg per mil is the same thing as 1 microgram per microliter. So if I put 0 microliters of BSA in there, I'm going to have 0 micrograms of BSA. If I put 10 microliters of a 1 microgram per microliter concentration of BSA, then effectively I've put in 10 micrograms. And this is kind of like a proportional type of multiplication. So essentially my corresponding micrograms of BSA will be 0 to 60 in increments of 10, just because of the way that we set this up. All right, so for your, that pretty much just kind of covers the table for your dye binding standard curve. And so for the next part, now we want to plot a standard curve of your absorbance values versus the micrograms of protein. And, that's just going to be a very simple XY scatter plot in which you are going to, computers freaking out a little bit right now. It's just an XY scatter plot, no connection of any lines or whatsoever. We're going to insert that in here in our Excel spreadsheet. Move this over to the side a little bit, and then just select our data in which we are going to have our X values be the 10 through 60 microgram BSA points. Remember that we don't plot the 0, 0 because that wasn't an actual data measurement. It was just used to blank our specs, and the corresponding Y values as well. That's a little weird. I should actually just, highlight the whole thing, reselect, and click OK. So I have that, and now I have, this TF data standard curve plot. I want to make sure that I add a trend line to this, and for my options, I want to set the intercept to 0, display the equation, and also the R squared value on my standard curve graph. I'm going to make this just a little bit smaller. So I pretty much have a you know, everything that I need in terms of a graph for my chapter, I should say, sorry, my prompt B5 exercise. Now, this is where things are going to get just a tiny bit difficult because we have to introduce error and we have to propagate it for the rest of our calculations. And so for prompt B6, now what we want is to report the protein concentrations for your DTNB reactions from prompt B4. Oh, I should say, sorry, in prompt B4, you should also include the experimental tube readings as well, not just the standard curve tube readings. Also include the experimental tube readings for prompt B4. But those tube readings that you had for the absorbances, now we're going to back calculate to mass and also further our calculations to protein concentrations, but there's going to be some error associated with this because it's going to be introduced from our standard curve. So in order to get the error in our standard curve, thankfully the only error that we need to worry about is the error in our slope and not our error in our intercept, our y-intercept, because we eliminated that by setting the slope to 0, is we need to perform a Linus function on Excel. And so if you know, you can follow along, great. If not, no worries, because I've also included that pertinent data here in the TF data. But if you want to do it on your own, you know, just basically follow along for the next 2 minutes. So what we need to do is find this Linus function is going to give us and report to us the slope and also the error in our slope so that we can start propagating some error in our next calculations. So the way that this works is that essentially what we need to do is highlight somewhere in our Excel spreadsheet a 2-column by 5-row designation. I believe that's what it is. And then what we have to do is type in Linus or equals Linus to start the formula, and then open a parentheses. It's going to ask you, what are your known y values? And remember, we always start with the actual values themselves. We don't start with 0 because that wasn't an actual measured value. It was only used to blank the spec. I'm going to highlight my known y values, put a comma, and then highlight the corresponding x values as well. For the constant, what we want to do is essentially have this be false. And so what we don't want to do is we don't want to add a y-intercept into our error because that's not what we have in our slope. So I'm going to put false here for that part there. And for the stats, I'll just go ahead and put true because I do want additional statistics aside from just the slope. The next part is a little tricky. So if you are a Mac user, I believe you need to hold down Command and then press Enter. But if you are a Windows user, you need to hold down Control and Shift and then press Enter. And if you do this correctly, which clearly I did not, all the corresponding values get propagated in here. I believe that I messed up in this part here. So in order to fix this, I'm going to re-highlight everything, go back to the formula, and I believe that what I want to do is probably not put false, but instead put 0. Maybe that's what I should have put. And then I'm going to hold Control, Shift, and hit Enter, and still didn't fix it. Maybe it's not that. I know. Re-highlight everything, the formula that I want to, maybe it's just nothing. Yeah, it's not nothing though. Thought it was 0. Oh, I messed up because, oops, sorry guys. I messed up because I went too far here. If I put 0, I think this is just supposed to be false. Control Shift Enter. Yeah, okay, that's what it was. So basically I went a little too far in selecting my corresponding x values. I did want to have that first part be false and that second part be true. But essentially, once you are done typing in your formula, Windows users hold down Control and Shift. Mac users, I believe it's hold down Command, and then go ahead and press Enter. When you do that, the entire highlighted area gets propagated with all the other statistical information that you need. This first two cells over on the left is going to tell you the slope and also the error in the slope. And then the next two cells are going to tell you the y-intercept and the error in the y-intercept. But because for the purposes of this biochemistry course, we don't allow any y-intercept values to occur because we want to obey Beer's law. If something has a sample is of 0 concentration, its absorbance should also be 0 as well. We're not going to have any B value or error to worry about. We're only going to have to worry about the slope and also its corresponding error. You will, if you do that function correctly, you will then come up with these two values here that you need. If you, for whatever reason, can't perform LINUST in your Excel sheet, do not worry. Those values are already just given to you from the get-go in the TF data Excel worksheet, which are right here. So you have the slope and also the slope error. So let me just kind of, these are the two values that we're going to need to start working on concentration. So I'm just going to remove now this standard curve here and remove this extra part here, and then just start working here on the TF data. So to figure this out, we need to back calculate going from absorbance to micrograms. And so I'm going to put another, this is actually going to be a little difficult to do. I'm trying to figure out how to do this effectively. All right, you know what I'm going to do? I'm just going to basically start over here. I'm going to delete all this stuff and then just start over here. So I'm going to put micrograms here, and then because these are going to have error calculations to them, I also want to put the error here as well. And I'll show you what that's going to look like in a second. So normally, if there wasn't any error associated to this, we would just pretty much take our absorbance values, divide by the slope, and then we would get our mass. Because our standard curve was plotted against micrograms, the mass is going to also be in micrograms as well. But we have error associated to this, so now we have to use our error propagation formulas. So you can do this by hand if you want to, but I don't recommend it because it does take up a lot of time. So what I've also included in a lot of the TF data that I posted on Blackboard is this error propagation calculator that I set up for your convenience. Basically, the way that this is going to work is that all the values that are inputted below, big A, big B, little b, are for this function right here. So you have big A and the error, and then you have some function with big B and little b as the error equals, and then the result, big C, little c. And big C, little c can be any of these four values here depending on what the actual function is that you wanted. So it calculates an addition between big A, and big B, little b. It also it also gives you the result if you wanted to perform a subtraction between these two. It also gives you the result if you wanted to perform a multiplication of these two, and also the division result between these two values as well. So let me just go ahead and show you how this calculator is going to work for you. So for example, if you wanted to figure out, I'm just trying to make all these windows fit here at this point. If you wanted to figure out what the mass, the corresponding mass was for DTNB reaction 3 from this absorbance values, again, you would normally take the absorbance value and divide by the slope, but now you have slope and error. There is no error in the absorbance. So this value here for big A, little a is going to be, I'm just going to put in here in this box here, 0.537. That is the absorbance value that I have. There is no error associated to this, so I'll just put 0 for little a. And then for big B, little b, this is where I'm going to put the slope and its error as well. So the slope for this was 0.017027, if I want to be precise. And the error for that was 0.000318. That's the error in the slope. And when I set this up correctly, 0.000318, yeah. When I set this up correctly, what I'm looking for now is the division between these two measurements and error. And what I want to pick up is this value right here. If I take big A, little a, and divide by big B, little b, the division answer will be right here. So this is basically what I want to take with me for the next calculations. So I'll go ahead and then just copy that and then just put that in my Excel data sheet. So now I have the associated micrograms and also the error for this absorbance because my slope also had error with it as well. And I am going to just really quickly do the rest of these values for you. My slope and its error don't need to change, so I'm just going to basically leave those values alone in my calculator and then input the corresponding next absorbance value here. So that is going to be 0.543. When I enter that, again, I'm looking for the division result. So this is the value that I'm going to copy and take over for my next calculations. And so essentially, and this is just going to help you. I could even go ahead and just copy this value here now and then just paste the text, the value text in there, and then just go ahead and copy this, continue to copy these values over again. Using this calculator is pretty much going to save me a world of headache when it comes to calculating these error propagation calculations. And so going ahead, I'm just going to copy that and then just paste the values. And then for the last one, I am going to do that last conversion from absorbance to mass using the slope and the error. So now for all of my 5 different experimental absorbance values, I have associated mass and also error. I need to find out what the concentration is though. So if I know the mass of that sample and I know the sample volume, I can just basically take this mass and error calculation and divide by the volume of my sample. So if what you're going to divide by does not have any error associated with it, you can also prove this to yourself using the formulas. Basically, if the denominator doesn't have an error associated to it, all you're going to do is just divide both the mass and the error mass. I should put here microgram error so not to confuse anybody. I can divide both of these by 100 and I'll get a correct value. I can just go ahead and show you that by taking this here, copying these values, and then just simply inserting them as just the values themselves, not pasting anything so I don't ruin the calculator. I'll just go ahead and put those values in there. And then my denominator, the B for the division, only has 100 microliters for the measurement, but no error associated to that. So I'll just go ahead and take out the error. And we essentially just basically get our answer for both the measurement and the error, but just divided by 100 because of the way that the formula works when there's no error in the denominator for a division step. So I don't need to really go through the calculator to do this. I could essentially just put microgram per microliter as the concentration. I'll leave a space for the error plus or minus symbol, and then I'll just put microgram per microliter error. And because of all of these samples were a 100 microliter sampling, I will basically just take everything and say equals that value divided by 100 for that entire column. And then, just include the plus minus symbol here for good measure. And then also divide the error by 100 to get the corresponding micrograms per microliter concentration. So I believe that is the end of prompt 6. So report the concentration micrograms per microliter for your DTNB reactions. Make sure to include the associated error for your concentrations that you provide. So that is pretty much going to be the end result for prompt B6 in the post-lab write-up. So going from absorbance to micrograms, you have to start incorporating error because your slope also has error with it as well. Like I said, use this error calculator that I provided for you. Otherwise, if you don't want to, you're just basically going to have to do everything by hand if you're going to be calculating these things without some sort of aid or something like that. Once you have your micrograms and the associated error for that, then essentially what you're going to do is just divide by the concentration of those reactions for those dye binding reactions, and then you'll get the associated, or I should say, you'll get the corresponding micrograms per microliter concentration and also the corresponding error of those micrograms per microliter concentrations. So this is pretty much going to be the answers that you'll report in in prompt B6. Now it says for prompt B7, for the GAPDH concentrations determinations from the DTNB reactions, basically telling you that those aliquots came directly from DTNB reactions themselves, meaning you don't have to take care of a factor of 2 quenching back calculation or anything like that. They came from the leftover reactions from your 3 mil DTNB reactions themselves. So the concentrations that you are reporting in prompt B6 reflect those in the 3 mil DTNB reactions. So if you know the concentration of those 3 mil DTNB reactions and you know the volume, then you can figure out what the total mass is and convert those total mass to moles. And so that is essentially what the essence of prompt B7 is. So we'll go ahead and start from our answers from prompt B6. So I'll just go ahead and just put prompt B6 here for a nice little label just to show what we're starting off with. And what we need to do is go from concentration to mass, and then from mass to moles. So that first step is, if this is the concentration for the 3 mils of the DTNB reaction and the total volume was 3 mils, then what we can do is multiply by the reaction volume, or by the sample volume, not the sample volume, yeah, like the reaction volume. And here, this is micrograms per microliter. So what I'm going to do is put here, we know that is the reaction volume was 3 mils, but another way of expressing 3 mils in microliters is pretty much 3,000 microliters. And this is true for all of them. So if we have a reaction volume of 3,000 microliters and we have our concentrations of micrograms per microliter, then what we can do is just multiply these values together to get our, what I'm going to say here is our total mass in micrograms. And this is going to be micrograms and also the error associated with those micrograms as well, because this is going to be a propagation of error again. Error. Whoops, too many R's. And I put in a symbol. So again, another trick to error propagation is that if you have a starting value with some associated error, and then you multiply the second value has no error to it, then essentially what you can just do is just multiply both the value and the error by 3000, and you don't have to do any error propagation or use the error propagation calculator. And essentially what we're going to then do is take that value right there and then multiply it by 3000 and do the same for everything. And also do that to the error as well. If there was an error in the volume here, we couldn't do this really easy step because we'd have to use the error propagation formulas. All right, so let's go ahead and just take a quick look at our values. So this is reporting to us micrograms. And it's saying that we, for value or the reactions 3, 4, and 6 and 7, we have about like 950 micrograms. And this actually makes sense because this is very, very close to 1,000 micrograms, which is the same thing as 1 milligram. And if you remember to how you set up your DTNB reactions, for reactions 3 through 7, you put in about 1 milligram of GAPDH protein into there. So these absorbance values are indicating how much protein there was in those DTNB reactions. And so it's reflecting actually very well as to how much there was in our actual reactions in terms of dye binding activity. But for reaction 5, this value is overblown. And the reason why it's overblown is because if you remember to how you set up reaction 5 for your DTNB reactions, this has SDS in it. We needed to put SDS in there to denature the GAPDH to get as many sulfhydryl groups as possible reacted with the DTNB. But because we took some of that sample and applied it to a dye binding assay, and SDS is an interfering substance in which it basically overblows the value, or it kind of like overskews the value such that it makes it look like there's more protein in there when there isn't. SDS will naturally give you a higher value for this sample here. So, don't be alarmed if reaction 5 calculation is way higher than all the others. That is very natural because of the effect that SDS has on the dye binding reagent. We're not done with prompt B7 just yet, even though we did calculate the total mass. Now we need to go and calculate the actual moles here. And so to do that, in the prompt itself, it said to convert the values, you need to use the GAPDH formula weight of 36,000 plus or minus 100 grams per mole. So I don't want to do a huge conversion. So this, pretty much 36,000 plus or minus 100 grams per mole is also the same thing as if we said it was micrograms per, I haven't set this up yet like that. Yeah, micrograms per micromole. So if we use this conversion here, 36,000 plus or minus 100 micrograms per micromole, then we know that our resulting values will also be in micromoles as well, according to this. And what we're going to do is take these values and their errors and divide by this conversion value and its error as well. So I'm going to go back to my error propagation calculator, and the first calculation I'm going to try to resolve is this 946.1444 plus or minus 17.670 micrograms divided by now this conversion of 36,000 plus or minus 100 micrograms per micromole. And the result that I have here now is the one that I'm looking after. I don't want to do addition or subtraction or multiplication between these two. I want to do division, and this is the value that I'm looking for. 0.02628 plus or minus 0.0005. So I'll just go ahead and just copy this as is, and then paste just the values in there, and I'll just squeeze this a little bit together just to be clear as to what is what. That's going to be micromole air. And that's basically what I am going to try to do for the rest of these values here. Because I set this up so nicely for myself, I can just go ahead and copy what I want to be the first value in error here, highlight all three of those cells, and just paste in the values. I can just go ahead and just start copying everything very quickly for my error, my values, my calculated values and errors for the micromoles. Then the next one will just be here, going like this, copy the values. This one again, of course, is going to be overblown because it has SDS in it. And then now what I'm going to do is take the rest, the last two, and calculate those micromoles and also those associated values. And hopefully no one chooses to do these calculations by hand, because they do take a while to even do with this calculation, this Excel propagation error calculator as well. All right, so here are my micromoles, my total micromoles of GAPDH in those 3 mL DTNB reactions, and also the associated error as well. But this needs to be done in nanomoles. So you want to make sure that you don't report micromoles, because not only did we ask you for nanomoles, but also this helps us out for the last calculation for the B section in the post-lab write-up. So again, this is just going to be a nanomole conversion. This is going to be the nanomole error plus or minus symbol just for good measure. And this, we know that there are 1,000 nanomoles for every micromole. So this conversion has no error associated with it. So when we're just going to multiply our micromoles and micromole errors by 1,000, we don't need to do the traditional error propagation calculation. We can just multiply both of these two different values by 1,000. So I'll just go ahead and do a formula where I can just take this entire column and just multiply it by 1,000 and do the same thing for the error as well. So these are going to be my final values for the TF data for DTNB reactions 3 through 7 in figuring out the total nanomoles of GAPDH for each of those reactions. I have about 26 to 25-ish nanomoles, and the associated error for the one that has SDS, naturally that is going to have many more nanomoles reported, because the SDS acts as an interfering substance for the dye binding assay. So these are going to be the 5 values that I'm going to report for prompt B7. Prompt B7 I'm going to put here. All right, so when I have my prompt B7 values, the last part for this tutorial video is going to show you how to take the averages of the non-skewed reactions. So reactions 3, 4, 6, and 7, because we're tossing out reaction 5 because that has SDS in it. So now for prompt B8, what we're going to do is just report one single average value. And that can get a little tricky if you are doing the traditional error propagation formulas. But essentially, what you would do is you would take this value. You have to add all except this one. You have to add these 4 values here using error propagation method, and then divide by 4 to get the average. So you could use the error propagation calculator and then add them in sequence, which would kind of, for the first part of this would look something like this, where you would take the first value and then take the second value and put it in this, the big B, little b cells. Take your addition. This is going to be your addition result. Now I want to copy that, substitute it in for A, and then take the third value, copy that, put it in for B, and then just continue this like little snowball effect that you're doing. Take the result of that, put it in for A, and then finally, put the last value in for B, take the result of this. So now this entire sum needs to get divided by 4, and you can put that result there. The number 4 doesn't have an error associated with it. And what we're looking for now is the division, the entire error propagation summation divided by 4 and giving us the division there. So the average value will be this right here. I'm just going to show you another trick to all of this. So for prompt B8, that is essentially going to be your answer there if you did all the error propagation for the averaging of those 4 values correctly. The issue is that can kind of trip you up a little bit, and most especially if you're doing it by hand, it's going to take forever. But just to kind of show you a different way of how to do this, if you are going to, for example, do big A plus or minus little a, and then also add that to big B plus or minus little b, and then add another value also with its error propagation, or sorry, with its associated error. And then finally, another value with its associated error, and then divide all this by 4 so you can get the average. This is going to take a while, even doing it by hand, or even, it's a little tricky to do it in the error propagation calculator. You don't need to do traditional error propagation for a sequence of summations. All you can basically do is just do big A plus big B plus big C plus capital D, and that will be your resolved summation. And then the error for that will then be plus or minus the square root of the squares of the sum, of all the individual squares of the error themselves. So that can just be kind of done in one fell swoop if you want to do that with a calculator. And then that can just pretty much summation of those values and errors divided by 4 will be your average. So I can basically show you what that looks like. The first part, again, will be the sum, or I could just put, the sum of this value, this value, this value, this value. If I hold down control, I can select multiple cells for a sum. And then I'm going to divide that by 4 because that's what the average is going to be. And of course, I got the same value that I got before when I used the error propagation calculator, plus or minus. And then I can just essentially, for a summation sequence for the errors, I can just take the square equals square root of this error to the power of 2 plus this error to the power of 2 plus this error to the power of 2 plus this error to the power of 2. Close that for the square root, and then don't forget to divide by 4 for the last part of the average, and I get the exact same number as I did before. So there are different methods for having to take these four values here for reactions 3, 4, 6, and 7, and finding the average value of the nanomoles and nanomoles error there. You can do it by hand if you want to. You can do it with the error propagation calculator, or you can just do that simple shortcut if you are just, for the most part, the numerator is just going to be a simple summation of values and errors. So this is the answer for prompt B8 in the error propagation calculation for the average nanomoles of GAPDH. The next video, which I'm just basically going to show you a little later with some commentary, is going to be how to solve prompt B9.